In order to really understand the universe, you can't just look at it, you have to have models to understand it. The way we do theory, the way we do these models now is to use large supercomputer simulations and try to build as realistic a model as we can that we can then compare directly to the observations that we have. So this is something that we had in from a very early point in the planning of ASTRO 3D, and we're actually one of the big teams within ASTRO 3D now. We've got connections into all the big projects.
So we're trying to really understand the formation of galaxies from a physical point of view. That's kind of the main objective that we have. Genesis is actually quite a big group. So there are people, for example, in Uni Melbourne, in Swinburne, here in UWA, and we're trying to focus on different aspects of ASTRO 3D. For example, the group in University of Melbourne, they're more focused on the epoch of reionization, so those first stars or first galaxies, and using our simulations to try to understand that. Here we're kind of more interested on the galaxy evolution aspect, so we want to see how we connect these observations of early galaxies to what we observe nowadays. So our simulations are kind of focused more on surveys like ASCAP, SAMI, some galaxy evolution.
We've got a very diverse team in terms of the expertise that we have, and that really is because the kind of theory that we need in order to supplement the surveys is broad in itself. So we have people who are experts in running these big simulations, n-body simulations, hydrodynamical simulations. We have people who are experts in developing the kind of algorithms we need in order to do these kinds of simulations, or in terms of modeling the physics that we want to include in these kinds of simulations.
Because our challenges are so big, we can't do this alone. So we need to make sure we use the expertise of everybody that is involved in the group. And that's to make sure that we're more than just the sum of our individual abilities, and we can actually, work together and take advantage of that.
My name is Kate Harborne. I am in the final year of my PhD. I'm a theoretical astrophysicist. I build models of galaxies inside computers and then observe them with my telescope, which is called SimSpin. Observations have this inherent and unfortunate limitation that they are a 2D projection of a 3-dimensional object. Imagine, if you will, that you've got a pizza. And you're looking down onto the surface of this pizza and you can see all the toppings, you can see the crust laid out in a big circle. But if you pick your pizza up and look at it edge on, all you can see is a line of crust and no toppings at all. So the same is true with galaxies, except for we can't pick our galaxy up, we can't move it around. We're stuck with one projection in the sky. Now, with my galaxy models that I build inside computers, I can manipulate them, I can project them at any angle you want and make an observation using SimSpin. And this means that I can help an observer determine whether or not that edge-on crust is actually just a pepperoni pizza or something new and exciting.
So my name is Lillian Garrett-Smithson and I'm a postdoctoral researcher. The main part of my role in the project is connecting large-scale simulations, theoretical models, to observational surveys. So these simulations might include 10,000 galaxies of Milky Way size or greater. And the benefit of simulations is you can follow the evolution of galaxies across the age of the universe, whereas in observations you're only looking at a snapshot in time. So they can really help with the interpretation of the results you get. So in particular, I've been focusing on the ASCAP Flash H1 absorption survey. So this survey is particularly fascinating because it's looking at the cold, dense gas in a galaxy, and it's also looking at a period of time in the universe when the global star formation rate is actually declining. So one of the main future challenges I see is that so currently we've been focusing on looking at absorption in systems that are in between ourselves on Earth and the source of the emitting photons. So in this case, this would be a luminous black hole in a galaxy. So we're looking really at those intervening galaxies between us and the source. But the next step would be to look at absorption from gas that's associated with the host galaxy of the black hole. And to do this, we'll need to think about modelling the black hole interaction with its surroundings in very great detail, which is still a very new, exciting area of research.
Something that is quite difficult is that the simulations we work with are very computationally expensive, and we are highly limited by the amount of computational time we get in Australia. So I think a challenge that we need to navigate well is how we use our international collaborations to help us have access to that additional computing time that we require. Love the group. I think the group is a very interesting group of people, internationalist people from everywhere, and we work quite in a collaborative way, and I really enjoy that, to actually know that every day I'm interacting with people. It's not that I go to my office and I'm there alone the whole day. I actually do interact with a lot of the team members every day. And that I really enjoy, actually, because it feels like we have this common goal and we're all working towards that.
It was a great opportunity to learn from some of the best scientists in the world.